Okay, let's do a node voltage example so that you can see that, again, everything is similar to what we did with chapter 4. So the circuit is given to us, IA, IB, and IC is basically being asked from us. So I'm going to go with this node being ground, defining this as ground. Let's call this node 1, let's call this node 2, and let's write the KCLs. So KCL at node 1, I'm going to have 10.6 coming in, so I'm going to write it as negative 10.6 with an angle of 0. IA is going out, so plus V1 minus 0 divided by 10 plus V1 minus V2 divided by 1 plus J2. Okay, so that's all I needed to write for the first KCL. For the second KCL, I write 2. I'm going to have, well, Ix is coming in, so, or let's write all the currents going out. So V2 minus V1 divided by 1 plus J2 is this plus V2 divided by negative J5, that's the impedance of the capacitor, plus V2 minus the voltage across the voltage at this point, which is basically 20 Ix, divided by 5 is going to be 0. So 2 equations, 3 unknowns. The third unknown is the Ix, so I have to define it. Ix is the current flowing here from node 1 to 2, so it's basically V1 minus V2 divided by 1 plus J2. So now I have 3 equations, 3 unknowns, and I'm ready to solve this. So I'm going to leave the math to you guys, and again, strongly recommend you to actually do the math yourself. And if you have any questions about like how to do it, let me know, or one of your TAs know. This is really complex number mathematics. This has nothing to do with the circuits analysis. So once you solve this, you're going to get V1 equal to 68.4 minus J16.8 volts. V2 is going to be equal to 68 minus J26 volts. Okay. Now that we have V1 and V2, I can find IA, IB, IC, and even IX. So for IA, I know that it's defined as the current flowing from node 1 to ground. So it's going to be V1 minus 0, which is ground, divided by 10. So it's just going to be 6.84 minus J 1.68 amperes. As for IB, it's defined as the current going from node 2 to flowing through the dependent voltage source. So it's going to be basically V2 minus 20 Ix divided by 5. So it's better to first define Ix. So Ix is going to be equal to V1 minus V2 divided by 1 plus J2. I have V1 and I have V2 and I have 1 plus J2. So if I use my calculator, I'm going to get 3.76 plus J 1.68. Now that I have Ix, I can actually come here and plug in the value of Ix, plug in the value of V2, divide everything by 5. I'm going to get negative 1.44 minus J 11.92. And this is in amperes. This is also in amperes. Last one is IC, which is the current that is flowing through the capacitor. So it's just V2 divided by negative J5. So it's going to be 5.2 plus J 13.6 amperes. Just to check our math, I can see that a KCL at this node tells me that the current of IA plus IX should be adding up to 10.6 and with an angle of 0. This is IA, this is IX. If I look at them, I can see that the imaginary parts are actually opposite of each other. So when I add IA and IX, they cancel out. And the real part, 6.84 plus 3.76, I'm going to get 10.6 on the dot. Okay, so again, for the node voltage analysis, all I did was the same thing that I did in chapter 4, except that I was dealing with complex numbers.